Right now we'll look at exponential growth and exponential decay. I'll show you that compound interest is exponential growth and what that looks like on a graph. We have looked at exponential functions before. An exponential function has x in the exponent. This is a very simple version of an exponential function. Y equals 2 to the power of x. X is plotted on this line, and this is the y-axis. So as x, the exponent, increases, the y value increases exponentially. The slope of this line keeps increasing. It starts off not growing very steeply. The line's not very steep here. Slope is low. It's positive, but it's very small. And the slope just keeps increasing. Up here, the line is very steep. Right? That's an exponential function. And then what I want you to understand now is that the formula for compound interest is actually also an exponential function. Let's write the formula down again. For compound interest, total amount equals principal amount times 1 plus interest rate to the power of time in years. Let's say we have a principal amount of 100. Let's invest 100 euros. We have a crazy interest rate of 50%. I pick that just because I want you to really see the exponential growth. If I make this too small, then it won't be noticeable on the graph. Okay, so we have we know that we put in 100 euros. We know that we're getting 50% interest. Our total amount, A, depends on the time that we keep this 100 euros in the bank, plus all the interest that's accumulating. We graph this function using time as the x-axis. So time we plot on the x-axis. So as the x value increases, the t value increases, time passes, more years get added, right? This here, what we usually call this the y-axis. Let's plot A, the total amount, on the y-axis. So we now have a function of t that is going to give us the total amount, right? Let's plug these values into our equation so that we know what kind of equation we are actually plotting. Total amount, still, it's a variable in our equation. Total amount, it equals the 100 euros we put in times 1 plus 50% to the power of t, and t is our variable. See how we have two variables here? Just like we do in a normal function, x and y, we have two variables here as well. Two variables that we plot along the axis. Okay, we can simplify this one step further. A equals 100 times 1.5 to the power of t. So this really is the equation that we want to show on this graph. We want to plot this equation on this graph. T is here. Let's find values for time equals 0. So the moment we put the money into the bank and nothing had happened yet. 1 year, 2 years, 3 years, 4 years, 5 years, and 6 years. And A is going to be our total amount after 0 years, total amount after 1 year, etc. I looked up all these values on my calculator so that I wouldn't waste your time. And then what we can do is plot the coordinates that we found. So when time equals 0, 0, our total amount equals 100. After 1 year, we had 150. After 2 years, 225. 225. After 3 years, 3 there. After 4 years, a bit more than 5. 5 years, 750 plus a bit. 6 years. Wait. Yeah, there we go. There we go. 6 years, 11, 40. So like there. Now if we draw our line, can't see my markers anymore. Voila. You can recognize the exponential shape in there. It has the same type of shape as this very simple exponential function. The slope of this line keeps increasing. The line becomes steeper and steeper, right? That shows the growth of our money when we keep it in the bank. So the longer we have it in there, the steeper the growth is. So the more we gain per year. See how we gain only 50 euros in the first year, and we gain this much in our 6th year. So that's an exponential growth. Let's see. Money is not the only thing that grows exponentially. There's different types of exponential growth. Exponential growth. Let's think of some examples, and then I'll give you a general formula that will work for any type of exponential growth. Well, the one example we have is money, like an investment. That we've looked at a lot. Another thing that grows exponentially is population. Like the world's population is growing by 1.1% each year, which means that the total number of people on the planet is the current number of people times 1 plus 0.011 to the power of however many years you wait. Let's say we only wait 1 year. So the current number of people, the current population of the earth, multiplied by 1.011, this does nothing now, is the total population after waiting only 1 year. It seems like a very small number, but if this happens every year, population grows exponentially. It's like an explosion. Another thing that grows exponentially is bacteria. This makes so much sense. It's really the same as population growth, right? Bacteria is just they multiply just like people do. Only bacteria do it faster. So if you start with 2 bacteria, they're going to have maybe 4 babies, which makes 6, but then all those 6 are each going to have 4 babies with each other, which you can tell that that's just going to grow more each day or hour. I don't know how long it takes bacteria. Right, so we want a formula that does not involve the letters for compound interest, because there's no principal amount, there's no interest rate, right? So if we want an exponential growth function that'll work for any of these types of exponential growth, we can say the final value equals the initial value. Let's say that's the initial value. So maybe the total number of people on the earth today, or the number of bacteria that we start out with. The initial value times 1 plus the rate of growth, right? We can still use R like that. Let's not, well, why don't we? Let's put T, rate of growth, as a decimal, and then T will be time, but it's not necessarily in years. Like bacteria, you wouldn't count per year. You know, you want to, you know, if you put bacteria in a petri dish, if that's what you call it, and you come back the next day, you're going to see growth already, right? So it's not a matter of years. Time could be in any unit here, right? Just make sure that your rate and your unit of time are the same, right? In interest, we say you get interest, you get 5% per year, and then time is also counted in years. But if this rate of bacteria growth, maybe that's a rate like of 50% per hour, then your time is going to be in hours as well. So these two have to have the same time unit. And if they don't, you need to change one of them so that they are the same time unit. Yeah? Very important. Okay, so this equation will work for any of these types of exponential growth. You'll need to do some problems where you plug in numbers and find other values, but I'm confident you know how to do that. Another thing I want to just touch upon is exponential growth. Things can grow exponentially. Of course, things can also decay exponentially. Exponential decay. Let's think of some examples. The value of a car. Yes. The value of a car. A car is expensive when you buy it. Just a year later, it's worth a lot less. And the longer you wait, the older your car is, the more the price will decrease. So it like doesn't decrease by 1,000 euros each year, but it decreases more and more. Shh. Yeah. Yeah. Okay, my child wants a banana. Voila. The value of a car. Also, temperature cooling. Okay. Temperature cools at a certain rate. Apparently. It's an exponential decay. Radioactive decay as well. Radioactive decay. So like temperature cooling, the fact that that's an exponential decay, that means that temperature cooling is not 2 degrees per hour, but you know, the first hour it's 2 degrees, and the second hour it drops 3 degrees, and the fourth hour it drops 4 degrees. It just keeps cooling off faster. That's what is meant by exponential decay. we can use the same equation that we just learned. The only difference is your rate of growth, because it is decay, your rate will be negative, right? So really all we need to add is when growth is actually decay, R is a negative number. Right? So if you add this to that, then your formula is going to work for all exponential growth and exponential decay. Okay, now I think it's time to do some problems on your own to practice. Good luck.